What we're talking about here is measures of dispersion. And so what dispersion means is how far the data is spread out. And so we care about that a lot. We can't just solely rely on the mean and the median. We care about how much our data is actually spread out. And we'll get into some examples that will explain that a little bit better. We're going to define these four things first. The first one is dispersion, which is in the title of this, and I've already said the definition of it. It's the degree to which the data are spread out. The degree to which the data are spread out. All right, an example I'm going to show here in a few minutes will help understand that a little bit better. The range, that is equal to R, and that's, I shouldn't put equal sign there. R is simply equal to the largest value minus the smallest value. So what the range does, you simply take the largest value and subtract the smallest value, and that tells you your range, where all your scores or observations fall within, which is a good measure of, it's an okay measure of dispersion, but it's not enough. So that's where we get to the next two: population standard deviation and sample standard deviation. So we're going to get into what these formulas are in a minute, but these are two important things that we'll be using the rest of the semester. All right, so population standard deviation, that's equal to sigma, which is just a circle with kind of a line on top. Okay, just as long as it looks something like that, it's no big deal. Just draw it as best you can. And then the sample standard deviation is equal to S. So we're going to define these coming up after this example I'm about to show. But I wanted to get out here what's important. We're looking at dispersion, the measure to which data is spread out. And then the range is a type of dispersion that we can look at. It's not entirely sufficient. It's okay to look at, but we need these two standard deviations to be able to talk better about our observations. So let's get into this example I want to show you. Suppose we have two graphs. Here's the first one, and down here I'm going to say IQ scores, IQ of the class. And here is the number of students. Then we're going to have a similar graph over here, and it's going to say the same exact things, but I'm going to draw it a little bit differently. IQ of the class and number of students. And these are all somewhat made up, but it gets the point across. So let's start out by values that we need on here. So right in the middle, let's put 100, 80, and then 60. Then over here we'll go up to 120 and 140. And then up the side, we can just 2, 4, 6, 8, and 10. We'll just stop there. And we'll do the same thing over here. So two identical graphs, but these are going to be two completely different scenarios. And what I want to show you is that when I'm done, you'll see that the means are the same, or the average is the same, but the data are spread out differently. So let's say here we have this. So the tallest bar will be around the 100, and then I'll just kind of make something up here, as long as they're the same on both sides. So just like that. So this tells me that my mean mu is equal to 100. All right, now for this graph, I'm going to do something similar. I'm going to just go up here and I'm going to stop about 6, roughly 6. And all the other bars are going to be exactly the same. So this is another scenario where your mean, mu, is equal to 100. This is a problem with finding the mean or the average of observation and only looking at it by itself. Both of these means are 100. Both of these observations are 100. But the difference is this data is less spread out than this data. This data is all even. We have the same amount of 50s, 60s, and 70s as we do 120s and 140s. Over here, we have more lower observations that are in these more extreme categories. So this is where the standard deviation and sample standard deviation come into play. They allow us to quantify how many people are in the range from, say, 90 to 110. They allow us to quantify the range of people between 180 and 120. So if we have that information, then we're able to tell if we have a graph bell-shaped like this or a graph that's uniformly shaped like this. So let's get into an example of the actual, let's first write the formula of the population standard deviation. So here, let's write population standard deviation again. Population standard deviation, and it's labeled as sigma. Again, just draw a circle with kind of a line attached on top, and you can also Google and look what it looks like. That is equal to kind of an ugly formula. We'll walk through one example, but it's important for you to know how to do this by hand, but it's also important to know how to do this in the calculator. We'll be using the calculator a lot to do most of these. So there are two formulas, really, but they're the same thing. So the one you'll see in textbooks will be, and watch me first because it's kind of big. You have the sum of the xi's, which means all the observations, minus mu, which is the population mean. So you're taking each observation and subtracting it from the mean, and then you're going to square whatever that value is, and then you sum all of those together, and then you divide by capital N, which is the total number of observations, and then you square root all of that. That is the standard deviation. Or you could have this. And again, you probably want to watch me, but this is called the computational formula, and this is easier, it's shorter to compute than this one. And so this one will be used if you're actually computing it by hand. Or you can do this, the sum of all the observations squared. So you square each observation and then add them all together, and then subtract that from the sum of all the observations, and that's squared. And then just that is divided by capital N. And then all of that is divided by capital N again. And then all of this is square rooted. And it seems like a lot, and it is, but once you do a couple examples, you see that this really isn't such a bad or long formula. So we're going to do one example of, I'm going to show you the computational formula, and then a subsequent video will show you how to use this in a calculator. So example 1. Your exam scores for the semester are, and I'm just going to say your exam scores are 62, 74, 87, 82, and 85. Find sigma, the standard deviation. So you may see, you'll just, anytime you see sigma, it means the population standard deviation, and that's important. Population Population means you're using mu. Okay, that's important. Population means you're using mu and this formula. When we get to the sample standard deviation, you'll use the notation for sample standard deviation. So find sigma. First thing we want to do is let's draw a t-chart. Let's say we have our scores here. Those are the xi's. All right, so let's just write those down. 62, 74, 87, 82, and 85. So based on this formula, on the computational formula, that's what this one's called. Computational formula, only thing we need to find out is we need to square each of the observations, and then we need to add all those together. And then up here we need to add all the observations and then square. So there's two different things here, two different squares, but they mean two different things. So let's look at, just take it step by step. Let's look at this one first. So what we're looking for here is we want the observations squared. So I just wrote xi quantity squared. So I'm going to take each of these numbers and I'm going to square it. That's all I'm doing. So for the first one, I'll actually write it out. 62 squared, that's equal to 3,844. And then I'm going to square 74, and I'm just going to write the answers down. 5,476. 87 squared, 7,569. 82 squared is 6,724. And 85 squared is 7,225. And now what this is saying is sum all of those together. So let's sum all those together, and you would get 30,838. So this takes care of this portion of the formula. And then the next thing you'd want to do, this says to sum all the observations and then square that number. So let's not worry about the square right here just yet. Just worry about summing all the observations. And then we'll plug everything into this formula and see what we get. So when you sum all of these together, just these five, you get 390. Now let's plug this into our formula. So let's write the formula first. So it's the sum of all the observations squared. So I'm squaring the observations and then summing them, which is this number here. And then I'm going to subtract the sum of all the observations and then square that number, which means we'll plug this number in here and then we'll square it. We'll do that one at a time, not all at the same time. And then that's divided by a capital N, and then this whole thing again is divided by capital N, and then this is square root. This is equal to, now let's start plugging in everything we know. The sum of all the x squareds is this number here, 30,838, minus the sum of all the xi squared. So let's just plug in all the observations, the sums of all the observations, which is 390, and then squared. So I'm just actually writing it in. That's divided by capital N. Capital N is the total number of observations, which is 5. And then all of that's divided by capital N again, which is 5, and then the square root of that. All right, so simplifying this, you get 3,838. So what I'm going to do is, in my calculator, I'll do 390 squared, and then I'll take that number and divide it by 5, and that gets me 30,420, 30420, and all of that's divided by 5, and we still have the square root there. And then I'm going to come over here to this bottom part of the page. That well, I don't need to do that. That gets me 9.14. We'll call it points. So that's our standard deviation of our exams here. So here, when I plug this in the calculator, you do 30,838 minus 30,420 divided by 5. And then you get, that would get you 83.6, and then you square root 83.6, and it gets you 9.14. The last thing we need to look at is the sample standard deviation. Now, I'm not going to do an example, but it works exactly the same way. Just one little difference here, or maybe two little differences here. So sample standard deviation. Sample standard deviation, we said, was equal to S. And so just watch me for a minute. You're going to have this divide line, and now you're going to sum all the observations minus the sample mean, which is x bar in this case, and all of that's squared. And then divide by, and here's the difference, n minus 1, and then square root of all that. The reason we have to divide by n minus 1 here is beyond the scope of this course, but to just tell you why it's there. We divide by n minus 1 because we have a sample. We're dealing with a sample. So that means we're going to have more variability in our results. So by subtracting 1 from the bottom, it makes our standard deviation bigger, which is a good thing in this case. Since our population's unknown, that's why we have to subtract this one. If there were other parameters that were unknown, then we would have to subtract another one from the bottom. But for this course, you just need to know that that's the formula. And then there's the computational formula, and it's roughly the same thing. But from now on, we're going to be plugging this one in the calculator. If I ask you anything on exam-wise, it will be to do the population most likely. So that's it for this one.